The laws of quantum physics, which govern how molecules interact with one another, have helped us develop technologies that we now take for granted, like lasers, MRI machines, and semiconductors. But we are now at the dawn of a new era of quantum computing.
This is a very big leap forward for humanity. It's a transformative technology.
Today's quantum computers are still quite crude, but some believe they have already achieved quantum supremacy, the ability to crack problems that conventional computers could never hope to solve.
The biggest supercomputer on the planet Earth today might take maybe 15 billion years to crack the kind of keys we use to have secret communication. A quantum computer can crack that in under a millisecond.
But this new era of computing could make the digital security systems that underpin much of the global economy obsolete, posing a massive worldwide cybersecurity threat.
You have billions of laptops and servers. You have billions of IoT devices. Every little camera that you see, that needs a software upgrade if it's going to remain secure.
So how can we reap the benefits of quantum tech while staying ahead of the risks it poses? We asked Jack Hidari, the CEO of Sandbox AQ and author of a best-selling guide to quantum computing.
The word quantum was coined by Max Planck in 1900 to identify a series of interactions that we see from experimental data that could not be explained by the old physics that we had. When a molecule meets a molecule, they don't meet like Newtonian billiard balls where they bounce off each other as if you were playing a game of pool. They interact not in a deterministic way, but in a probabilistic way. Quantum explains the fundamental nature of our universe, that we don't have a fixed sense. If this happens, then this exact thing will happen after that. In fact, no, we now understand that our world is probabilistic.
So how does this apply to computers? Conventional computers use the set cause and effect logic of classical or deterministic physics, while quantum computers rely on the rules of probability, which means they can explore the gray areas of uncertain outcomes. But to do that, these computers need to be built very differently.
Most of us know that today's computers run on bits. Bits is a short word for binary digits, just a 1 or a 0. It's a flip on or off. But a quantum computer works in a very different way. In a quantum computer, the core logical unit is a qubit, a quantum bit. Just like a bit, a qubit can take on the value of 0 and 1, but can also take on what we call the superposition of 0 and 1. What exactly does that mean? Well, from a math point of view, all it means is that we might have a 50-50 scenario where we put the qubit in a superposition of 0 and 1, such that when we take a measurement of that qubit, it has a 50% chance of being a 1 and a 50% chance of being a 0. That is one kind of superposition. But you can also have a superposition that's 75 and 25, or 80 and 20. And because we can have a number of qubits and put them all into superposition, and then in fact entangle some qubits together, we can have a very, very powerful computational engine.
If superposition means that qubits can hold the value of 1 and 0 at the same time and in different proportions, then what is entanglement exactly? Picture a jumble of electrical cords. The basic idea is that while two cords are individual objects, two entangled cords are in a state that connects them to one another. Inside a quantum computer, individual qubits can also be entangled. But because qubits obey the laws of quantum mechanics, entanglement doesn't just connect them, it brings the qubits into sync with one another. As a result, if you were to measure the superposition of one entangled qubit, you could instantly know the superposition of other qubits it is entangled with, opening up a whole new world of computational possibilities. This is the magic of quantum entanglement.
One qubit added to a quantum computer doubles the representational power of the computer. This is a very, very powerful thing that we don't have in the old world. Ultimately, we'll all be able to access these kinds of quantum computers on the cloud. That's what's very different about this computing revolution. In previous times, over the last 30 years, you had to buy the new kinds of machines. But the quantum revolution is mainly happening in the cloud. And all the major cloud providers now, they're all starting to provide easy access to quantum computers. Those quantum computers of today are quite primitive, quite early, but what that means is that as they scale over time, you will get access. Students are getting access right now for free, and corporations are getting access for pretty inexpensive prices
Through quantum computers, a concept once confined to theoretical physics is making strides towards becoming part of our everyday lives. We stand on the threshold of unimaginable computational power, begging the question, what will this power be used for?
If you want to develop new drugs faster, you need to think about quantum. Right now, it takes 10 to 15 years to get a drug from molecule to medicine. Quantum equations in simulation, that is, simulating the molecule, can accelerate drug discovery very significantly. Each time we run the simulation, we can change the molecule just a little bit. We then synthesize it in a real lab. We test it. And only then do we go into human trials. This will not only speed up, but it will improve the nature of how we develop drugs. In a world of quantum, I think we're going to have massive innovation in clean tech. One way of doing that is to improve the chemistry of the kind of batteries that we need for electric vehicles. Elements like cobalt, for example, are hard to get at in many parts of the world. Instead of tinkering in the lab day after day with different possible chemistries, we can accelerate this process. We can simulate these different ions in a battery in a quantum simulation. Then we can prototype those in the real world and test those on actual cars and test them in large buildings. Today, almost no home anywhere in the world and almost no office building or factory has a big battery. But by having quantum technology, we can have widespread storage in the electric grid.
While quantum computing has huge potential upsides, we also need to prepare for the challenges it will pose. One priority is something called post-quantum cryptography, the development of an entirely new cybersecurity system, strong enough for the quantum age.
One of the most important existential threats to our cybersecurity, to our data, is the quantum computer itself. Quantum computers will break the encryption that we use today. That encryption, known as RSA, has been with us for a long time. When you send a credit card over the internet and buy something that is using RSA technology, the biggest supercomputer on the planet Earth today might take maybe 15 billion years to crack one of these keys. But a quantum computer, not one of today, but one that is scaled, can crack that RSA key in under a millisecond. Quantum computers are so powerful in this area. We will eventually have to upgrade the software on 20 billion devices around the world. So this is a major undertaking. It's going to take years to move to the new standards. One of the reasons why this transition to post-RSA security is so urgent is an attack known as Store Now, Decrypt Later. Acronym is SNDL. It means that adversaries, hackers, be it state-sponsored or independent, are hacking into other networks, corporate networks, government networks, personal networks, and they're grabbing information that is encrypted with today's technology, RSA. And they're storing that information for the day that they have more advanced computing to read that. And even if it's years from now, that information is very valuable. The good news is that 40 of the leading governments of the world got together and they said, this crisis is coming. We need to have a standard that we can use for confidential information that will take us beyond the RSA standard. And so we're going to get these standards, these new protocols that allow us to communicate and protect against the quantum attack. And that is why all 8 billion people on this planet eventually will upgrade to this new technology.